So this is my talk that should have been presented in ISBRA in October, and on October 7, October 7 night, I had a flight to ISBRA, and as I hope many of you know, this flight didn't take place, and so this is the first time I give that talk in audience. Not too many. It was given, but on a Zoom. Anyway, so yeah, and it is dedicated to the Israeli hostages by Hamas in Gaza, and it seems that they are overlooked by whatever politics. Anyway, so let's start. So the nice thing about this, in general, this theme is that it will comply with some very naturally with some talk that was given here later on, and it actually encompasses and spans a very wide spectrum from pure combinatorics to hardcore complexity and algorithms, but to very vivid biology and relevant biology. So let's just start. So we see here a phylogeny, and it represents the evolutionary history of the species that we see. Leaves represent living species. Internal nodes represent extinct species or points of speciation events. And the branches, the structure of the tree, represents evolutionary relationships. So this is quite known, and let's see how the talk is outlined. So we start with the supertree construction that is very, very popular, in particular nowadays when we have so many trees and so many data and so many conflicts between the trees. So we'll discuss that. We'll start with the rooted supertree with the MinCut approach versus the MaxCut. Then we'll move on, we'll extend to unrooted supertree, and we'll see the quartet MaxCut that is embedded in many algorithms and implementations. And we'll move to some theoretical results about the theory behind the practical algorithms. Like Kenneth just spoke, there is a lot of theory of everyday's algorithms. And then we go back to biology. So let's start. Okay, and yeah, not too many technical details because we want to somehow keep you interested. Okay, so let's start with the supertree construction. And the idea is the following. So in standard phylogenetics or in comparative genomics in general, we normally have representing orthologous genes for the species we are after, and the idea is to infer the tree or the history of the sequences or the organisms that stand behind the sequences. However, sometimes we don't have such homologous sequences for all the sets. So sometimes these 1, 3, and 5 have gene A, but we don't have gene A, or these organisms don't have gene A, and they have instead gene B. And moreover, data can come from sources that are entirely non-molecular, and we want to, in the supertree approach, we want to spill in all the information we can in order to infer, to take the most information that we can into the reconstruction, okay, like morphological, behavioral, and moreover. So we would like to use all this data, that is, build separate trees and combine them. So this is the idea, to build separate trees and then combine them together. So this is the supertree approach. So it aims to combining all these trees on overlapping species into one tree over the entire species. So we normally call it big tree from many small tree. Okay, so let's see an example, a more vivid example. So we have these trees. You see, this is over human, these are over fish, and we want to build some tree, and we need that overlap. You see that overlap there with the human and the fish. We need that overlap in order to really combine that together. So what we do, we combine that so every tree, every small tree is represented inside that big tree. And soon we will dive into the details. Okay, so with rooted trees, we have a root and the time notion is present. So we know the time, we know what is what follows each event, and so the standard, the least common ancestor is the principle here, and the basic reconstruction unit is a rooted triplet. Okay, so with that rooted triplet, we can actually, it's like a bit of information, the least information that we have. In the unrooted setting, we don't have a root, we don't have the time notion. We don't know where to place the root. And trees are represented by splits. If we take some edge, the tree is splitted into two components, and this is the information that we have. And here the most basic information is an unrooted quartet. This thing that only tells us that these two guys are not necessarily closer to each other, rather they're separated by a path on the big tree, okay, from these two guys, and vice versa. Okay, so this is the difference between rooted and unrooted. Okay, so what is the underlying supertree approach? We get several trees that normally, but not necessarily, are conflicting. So you see these are the trees of different sizes, and we decompose them into the most basic components, like here, as I said, the rooted triplet, and now we combine them. Now we combine them together, the triplet, and we wish to see how much these triplets are represented here. Okay, how much this combination or this summarization really represent our input. So this is the goodness of that reconstruction, the supertree reconstruction. Okay, so it's suitable also for large-scale phylogenetic reconstruction, where we have all the information, but we decompose it into small subunits, and we build small trees and join them together. Okay, so there are several steps here. That step is purely, in a way, combinatorial. It is not so much about parameters, just to combine these pieces together. Okay, so very surprisingly to me, when I started with this in my PhD, so I found it's not me that found that, but I found that there is actually an algorithm that goes back from database theory that deals with that problem, and it is by Eho et al. And this is how it works. See, it's so elegant. It's so simple, so elegant, and this is how it solves. So it's like basic algorithm class for first year algorithm. Okay, so we have these guys. So we have these guys, and we call it the connectivity graph. Have a look. And now we have the evolution over these guys. Okay, the evolutionary hints, or the evolutionary signal. And we see the primates that they are, or the fish that is an outgroup to the primates. So we join the two primates in our connectivity graph. It's the connectivity graph over the set of species. It's so elegant. It's so simple, so elegant. So we join them here. Now we have another information. We have the two fish that are closer to each other, or that are closer to each other than the baby. So we join the two fish on that connectivity graph. We join them. So let's see something more concrete. Okay, so we have now, this is the input. We have 6 guys and how many? Like 5 triplets over these 6 guys. Let's build the connectivity graph. So here are the 6 guys, and now let's go over every triplet. So we start from the first one, and we join 1 and 2. You see 1 and 2, we join them in the connectivity graph. Next, we join 2 and 3 because of that second triplet. 4 and 1, 1 and 3, and lastly 6 and 5. That's it. This is the connectivity graph that is inferred, induced by that input, that evolutionary input. So what we do, it is a recursive algorithm, very nice, very elegant. So we have that connectivity graph, and now while we decompose the organisms or the elements, we build the evolutionary tree. So we introduce a new tree node, ancestral node, and we hang the component below that or under that tree node. So here we hang 5 and 6, and we cannot do anything about it. There is no information here on 2 guys, so we just hang them below. But here we have these 4 elements from this connected component, and we have that information. These are the triplets that belong to these guys. Let's see how we do that. So first we hang 5 and 6. Okay, we hang 5 and 6. No more information here. But let's see how we did that, and everything here is recursive. So it's like, really like, even for a programming course, something so nice to program and to train your students in Python and recursive Python and algorithms and combinatorics. Okay, so we have these guys here. Again, the connectivity graph over 1, 2, 3, and 4. And we have these 2 triplets. So we join 1 and 2, and then 2 and 3. So we have 2 connected components. 4 versus 1, 2, 3. So again, ancestral node here, 4 will be hanged here, and the 3 others there. Okay, let's see. Here 4, and then 1, 2, 3, and that triplet of 1, 2, 3 that we hang here. 1, 2, 3. Okay, this is U sub 2, U sub 2. This is what we have on the right side. And this is the entire tree. So this is the entire tree where every triplet is represented here. And you can check that later on. Okay, so life is not so simple, or maximum triplet consistency. So in many cases, actually always, in life is not that elegant, or life is elegant, but it's not that simple. So, and the triplets are incompatible. There is no tree that resolves all of them. And we will see in biology how these conflicts come. So it just adds more, I would say, beauty, but complexity into life. So take these 3 guys, and let's build the connectivity graph over 1, 2, 3, 4. 1, 2, 4 here. Now 3, 2, and now 4, 2. Okay? One connected component. We cannot decompose. We cannot hang the 2 components on both sides of the ancestral node. What we do, okay? So this is the maximum triplet consistency. Find a tree that actually resolves the maximum number of triplets. So we need to resolve the maximum. So some tree, any tree over these guys, over these leaves, that resolves the most of the triplets. And we can be sure we will not have a tree that satisfies all of them. Because of that algorithm, one triplet needs to be violated here. So this is actually NP-hard problem. There is some reduction from feedback arc set. So like I told you, I mean, there is, but this you will find everywhere, that people find problems that are NP-hard. And, you know, I started my, it's more than, yeah, it's almost 25 years since I started my in computational biology. So I'm among the more veterans here, or the older one. And I remember my adored advisor told me that when he introduced me to that field, he said, okay, so everything is NP-hard, and what shall we do? Shall we just sit on our seat and scratch our bottom? And this, yeah, I mean, yeah, like I said, my beloved advisor. And anyway, so the thing is to come with solutions. This was his message, to come with solutions. And actually, he was, again, among the first two. So in parallel, two teams came with actually the same idea that is called the MinCut heuristic. And the MinCut heuristic says the following. Since every triplet in that connectivity graph is represented by one edge, let's look. So and we need to violate at least one triplet. Let's look to violate the least ones, the least numbers. Okay? And this is the idea. So let's see here. So we have, this is that same example that we, this is an example with conflicts. This is the connected component. It is one connected component, so there is a conflict between these guys. And now we want to minimize the violations. So we need to somehow to break or to separate or to partition the guys and to continue in the recursion. So we just compute MinCut here, not to cut the least number. So let's apply now the MinCut heuristic. So we partition one. So we just violate this triplet. We partition one, we hang it on one side, and then move on to the rest of the guys. So we violated this one because we separated one from two, where one and two need to be together. And now we continue, and we violate another triplet, and another triplet, and that's it. And this gives, and you satisfy these guys, but this tree is not binary anyway. So this is the resulted tree that is represented by this approach. And I remember, again, I was a PhD student, like some of you here, and you know, we like to play with the, if we get some elegant problems, we like to play with them. And I said to myself, hey, but there is something much more, there is much more structure here. Why this approach? Why this greedy approach? Why not something that is more? And then I came with this idea, and let's see, again, as a PhD student, so it's more than 20 years back. So a key observation here is that at every step, when the algorithm is stuck, some triplets are violated. Some triplets, when you separate one from the rest, we violate a triplet. But on the other hand, we can satisfy. And let's try to satisfy the most. So for a triplet ijk, denote the original edge, the edge by by the min cut approach as a bad edge that we really don't want to cut. And let's color them with red. But some are satisfied. And and now introduce more information into the problem, and with these good edges of ik and jk. These guys, these edges, we do want to cut and to separate, because the key observation is, let's look at it later. So these are the new good edges and the bad edges. So we added to the bad edges, the red edges, the good edges. And the key observation here is every triplet, ij bar k, such that we don't violate I and j. We don't cut that. We don't separate that edge, but we do separate either this one or that one. That triplet is satisfied. And the idea is to find a cut that maximizes the ratio between good and bad edges. And this is again just a heuristic. It's just a heuristic. And until now, all this is like some games in simple algorithms. But you may want to see how practical it is and how useful in biology. Okay, so this is the tree, this is the cut, the separation. And actually, after separating that edge with the MaxCut, we call it, we actually we violated one triplet, but resolved all the rest, and that's it. The game is over. No triplet was left. So it also accelerates substantially the running time, instead of just running more and more min cuts that are not so useful. Okay, so how we actually formalize that into mathematics? So this is the idea. We have good edges, we have bad edges here. We look for the ratio between them, and we run the MaxCut. Okay? However, this is equivalent to solving MaxCut, and I am not sure how familiar you are with this problem, but MaxCut is among the most studied hard problems, and that there are so many on graphs, so many problems that are related to MaxCut. It's a very celebrated problem in theory, in practice, wherever you want. So there are some exact algorithms, but the exact algorithms are, of course, approximation, because we deal with some NP-hard problem, but even the approximation is very hard computationally. Okay, so what we do is somehow to give some heuristic to this, and the heuristic is inspired by semi-definite programming. And here I joined my host Satish Rao from Berkeley, and we came with some semi-definite programming like heuristic that appeared to be extremely fast and efficient, and implemented the MaxCut idea. So it's some heuristic over a heuristic, because the MaxCut is a heuristic and the SDP is a heuristic. But you need to actually control somehow, and it turned out to be really fast and efficient. Efficient in terms of performance. Okay, so let's see the example. So we have the example here. This is our instance of this toy example of 6 elements, and that are by these rooted triplets. And this is how we map them. This is our SDP, and we have the blue edges that we want to be the longest that we can, and these guys, the red edges, short as much as possible. And now when we draw a random hyperplane on that circle, the likelihood to separate or to cut the blue edges is high. Okay, so you see this is the mapping from combinatorial or discrete representation to some continuous representation over the plane. And these are quite celebrated and common algorithms of cutting a sphere or partitioning a sphere. And now we get into the harder task, that is unrooted trees. Okay, so inferring rooted trees is problematic. Ordinary reconstruction infers unrooted trees. So triplets are useless here. We don't have any information here, any phylogenetic information. And then what we work is quartets. So we work with quartets. And here, so Satish and I, we came with that idea with the triplets, of the MaxCut with the triplets. But here, some more sophistication, more complexity arose, and we had to deal with this. So let's see what we do. Okay. So this is the quartet, and the information here is that is only that it splits, the quartet splits 1 and 2 from 3 and 4. Okay, only that we have that split. Okay. Something about quartet. Quartet amalgamation stands at the heart of almost any phylogenetic task. So when you hear a lot about phylogenetics and consistency and so many things, if you delve into the basics, you eventually find quartets. Okay? And this is normally Tandy, Wanau, that was here, probably spoke about quartets. This is among algorithmic guys in phylogenetics. Quartet is quite popular, and this is something worth knowing. So we don't have such an elegant algorithm like the AHO, and that is no wonder, because this problem is NP hard in general. Even if the quartets agree, we don't have an efficient algorithms to join them. This is something very strong, and I would say even unique, that even the decision problem is hard. Quartets introduce non-trivial obstacles for working with cuts. And what are the results that we achieved here? We build the quartets graph G of Q, where Q is the set of the input. And for that G of Q, we devised an independent divide and conquer algorithm. So sort of extension of the AHO et al. Algorithm, although we don't have here the time or the routing. And what is the quartet extension? Again, these are the bad edges that represent that we don't want to separate 1 from 2 or 3 from 4. And these are the good edges that we do want to cut them. We do want to separate 1 from 3 and 2 from 4, and so and so. And again, we give a unitary weight to the good edges, and we adjust the weight of a negative weight of the bad edges. And again, the motivation is that a maximum cut will strive to cut these guys, but not these guys, that reduce the value of the cut. Okay, so this is the quartet graph. So all these quartets somehow combined and build a big connectivity graph. So this is the quartet graph, this is the connectivity graph. We have here jointly bad and good edges, and here we run the same MaxCut algorithm. Okay. Now, how do we adjust actually the algorithm? Some technicality, and I want to move forward from here. So when we deal with triplets, we have only one possibility. So, or two possibilities. One, that the triplet is, like here, the triplet is violated. We separate 1 from 2, that's it. Or that we satisfy that triplet. However, here we have one more complicated case. So either that we violate, we cut these 2 bad edges, we separate 1 from 2 and 3 from 4, or that we satisfy, but we have another case here. This is the deferred edge. And this gave rise to the challenge how to remember these deferred quartets. The challenge is how to cope with these deferred quartets. And using some algorithmic techniques, we could show that if all cuts are found correctly, the correct tree is returned. But this is the if here, because we don't know how to find cuts correctly, and this is why, again, all this is still a heuristic. So the big challenge is to translate theory to practice, and quartets arise whenever signals conflict. We'll get to it. Can we translate the theory to some useful algorithms? And this is some work by, ongoing work by a student of mine that is 9 months now in reserve duty. So the work is stuck. And this is how the quartets, the MaxCut is actually handling data both in terms of accuracy and in terms of time. Okay, and you see that we deal here with very big instances. Okay, so this is some practical notes about how that heuristic is, or how useful is that heuristic. Now let's move to some theoretical results. And normally, so I like to speak about theoretical results here because the beauty of quartets is that it gives rise both to theory and both to practicality and to software and to generate software and to apply it. So it's very quartet. And when I came into this area, I play with the combinatorics, with the ideas, with the algorithms, but it turned out to be really useful, and that is why we generated that software. But also the theoretical results are important here because they shed light on very fundamental properties in phylogenetics. So let's see. So MQC, maximum quartet consistency, is NP-hard. By the way, how much time do I have? Someone knows the time? I assume something like what? Someone? Well, let's take 10 minutes more. So exact polynomial algorithms exist for special cases, and the only rigorous approximation was some pitas like 25 years ago, and then we came with some idea that actually formalized the MaxCut as a theoretical algorithm that can push the limit, can push the limit of the known results on quartets that are open for like 40 years now. And we came with the sampled SQC, sampled MQC. Let me skip on the details. We came later with some more refined approximation. Let me skip that algorithm, that sampled MQC. But again, when all this theory actually translated into practice, you get some idea of what you cannot expect when sampling. And sampling nowadays is the method of choice in phylogenetics. Sampling is everywhere. So again, we build the quartet graph. And we broke the bound of the 1/3 that is achieved. The 1/3 is some bound that is now, 40 years exists that bound. So that was the first time to break that bound, but on sampled triplets. Let me skip also these very theoretical results. But I want now to speak a little bit, like I said, back to biology. So quartets are, like I said, quartets are very present in the scene of horizontal gene transfer. When you say horizontal gene transfer, suddenly the audience wakes up. So I didn't see any wake up here. But when you speak with biologists, horizontal gene transfer is a big deal because it's all over. As Itai said, it is connected to antibiotic resistance. It is connected to toxicity. Horizontal gene transfer is everywhere in microbiology and in medicine. So the transfer of genetic material, not through linear descent. So I think Itai used very similar slide of the three causes of gene transfer: viruses, plasmids, and so he focused only on plasmids, but there are two more causes of gene transfer. And this is a significant mechanism by which bacteria acquire antibiotic resistance and also conquering niches. But we model gene transfer by several approaches. And this approach we model over the three edges. So the gene transfer is reflected by horizontal edge connecting two vertical edges. So this is the transfer. And it means that this guy here got this gene from that guy. So actually, its ancestor on this gene is not this species, this extinct species, rather from here. So it changes the tree. So the tree is different. It introduces conflicts. Okay? And the tree of life became network of life. And in '99, there was a big note in Science News and Science, I think, and it says new information, new genetic information mystifies microbiologists regarding unexpected old connections. And these are the connections from very old connections. Here the chloroplast, and here this is the mitochondria. All of these are resulted of very old gene transfer. But gene transfer is everywhere, actually, and all the time. So, 2 minutes? 10 minutes? 2 minutes. 2 minutes. OK, great. So so the goal here is that we want to reconstruct the microbial phylogeny, and we have a gene tree for every gene representing the evolution of this gene. And we cannot join all gene trees, okay, because it's a hard problem. So actually, we come with, let me skip into that positive theoretical results that also started from the ancestral of CGSI. It was here at IPAM with Sebastian Roch and myself. And we came with that approach of the majority vote. So every tree or every quartet actually have a vote. So this tree votes over this quartet by joining 1 and 4 versus 2 and 3. So all these are the algorithmic details. But the theorem here is that we can actually tolerate a very high rate of gene transfer and still reconstruct the correct tree. Let me just move to the conclusion and the main issues. So we saw that the MaxCut is actually superior to the MinCut. By the take-home message of the entire approach is actually to use the most information that we can find in the input, not to take partial information, rather to try to combine everything in a one framework. So this is the superiority. Analytical results, significant advances. Crucial component in gene phylogeny. So we want to combine trees. Gene transfer is everywhere, and we want to combine it into some information. And let me just, so 3 distances, quartet plurality, and open problem that just recently this year there was some breakthrough, and we are excited about this breakthrough. I would not go into details. I want now to acknowledge. So I started all this with Satish Rao, with Rafi Yuster from our university. I still work quite heavily on quartets because all the niceness. Sebastian that was here and now in Wisconsin. Tandy Warno that is here every year from Urbana-Champaign. These are my students, Eliran, Shai. Eliran and Shai were here in CGSI several times, Reuven Cohen, and the foundation. Okay, thank you so much.